I'm Pekka Ilmakunnas. I'm a professor of economics at Aalto University and member of the board of Finnish Academy of Science and Letters. And our first talk today is by Alexandros Iosifidis, pronounced well, and that's about teaching machines and object recognition. So, please.
Hello everyone, my name is Alexandros Iosifidis and I am postdoc in the Department of Signal Processing of the Tampere University of Technology. Today I will give you a presentation on how we can teach machines to recognize objects and actions. The topics that will be covered briefly today are image classification, object detection and classification in images, and action recognition. The methods that I will describe today can find applications in video surveillance, security, robotic systems. They can find applications in our smartphones, smart houses, and other smart applications. And we hope that they can lead us to a better life in the future. First of all, let us distinguish between the image classification and the object detection problem. As we can see in the left image, we have an image and we want to decide if this image depicts an object. In this case, we have classified the image as a dog image. The object detection problem is a more complicated problem where the objective is not only to classify the image as an image containing some objects, but we want to localize the objects in the image. We will start with image classification techniques. Most of the image classification techniques are formed by two processing steps. The first step is to represent the image using a vectorial representation usually, and afterwards we want to use this vectorial representation in order to classify the image in one of pre-decided classes. This is the traditional pipeline of image classification techniques. We have an image, we use an image description technique in order to describe the image based on shape, color, and texture information. Then we use a set of predefined prototypes in order to quantize the descriptors extracted for this image, and we obtain a histogram based representation. After obtaining this representation, we can train a classifier in order to be used afterwards to classify new unknown images. The current state-of-the-art approach combines these two processing steps, and we do it usually in the current state-of-the-art approach. We use it by using CNN networks, convolutional neural networks. This is a particular type of neural networks which can be fed by an image or a volume, and it can create an image representation which can be used afterwards by a multi-layer perceptron for classification. And now let us see an architecture of CNN. This particular CNN is formed by two convolutional layers and three fully connected layers. As we can see, the CNN takes as input an image, it applies several processing steps, and at the final stage we have a vectorial representation which is used for classification. Now I will describe you which are the basic processing steps for these two types of layers. As we previously said, we have an image and we want to apply a convolution for the first CNN layer. So we have a set of filters and we want to convolve this image with one of the filters. What we do is that we place the filter on top of a pixel and we multiply the elements of the filter with the intensity values of the neighborhood of this pixel in the image, and we sum up the result. We do it for all the pixels in the image, and we come up with a convolution image, which can have the form of this image. As we can see here, this particular filter can preserve the texture of the image. After doing this, we apply a pooling operator in order to summarize the information in small neighborhoods of the pixels. We do this for a number of layers, and then we come up with a vectorial representation, which is used for multilayer perceptron-based classification. This type of layers are called fully connected layers, and as the name denotes, they are formed by some neurons which are connected to all the neurons of the previous and the next layer with a set of weights. After having determined the architecture of our network, we want to teach it, to train it, in order to be able to correctly classify new images. So what we want to do is to feed an image to the network, which the network has not seen previously, and the network should be able to correctly recognize the classes that the image belongs to. How we are doing this? We randomly initialize the weights and the filters of the network, and then we introduce a set of images for which we know the classes that they belong to. For example, let us assume that we have fed one image. This image has been convolved for several layers, and then we end up with this vectorial representation. This is the input of the first layer of the MLP, of the multilayer perceptron, and we get the output of the network, which might be something like this, 0.8. What we do next is that we compare this output with the output that we want the network to produce. As we can see here, we have an error of 0.8. So what we do is that we update the weights of the network, so as if we feed again the same image, the output of the network will be closer to the desired output. Afterwards, we feed another image, we get the output, we compare it with the output, the desired output of the network, and we update again the weights. We do this for thousands or maybe millions of iterations, and finally, the network is able to correctly recognize the images of our training set. Here we can see what is the evolution of neural networks for image classification. This is a schematic representation of the standard pipeline, where we have the image, we have a type of descriptors, the bag of words encoding, and the classifier. Here we can see the architecture of CNN networks that have been used up to 2012, and here we can see how deep these networks have become lately. So what we want to do for detection is to localize objects in an image. So having a pipeline for image classification, we can use it in order to classify sub-images of the original image. So what we do is that we take this sub-image, we feed it to the CNN, and we classify it to some classes. So we decide if this image contains a dog, for example. Then we go to the next window. We classify this window. Then we go to the next window. And we do this for all possible windows in an image. However, this operation is very time consuming because the number of all possible windows in an image is enormous. So what we want to do is to reduce the number of boxes of windows that we will introduce to our classifier in order to fasten up the process. And here is where object proposal techniques have been proposed for. The idea of object proposal techniques is to minimize the number of proposed regions to be classified, and these proposals, these windows, should contain all the objects in the image. There are several challenges that should be addressed by these methods. For example, objects have a variety of shapes, sizes, and colors. We may observe objects by different viewing angles, and their appearance will be different. Also, there are multiple objects in an image. So object proposal techniques should be able to address all these challenges. There are two types of object proposal techniques. The first category exploits the observation that all objects are formed by smaller regions which are of relatively constant color. What does this mean? This means that if we over-segment an image and we create very small regions of uniform color, and then we combine these regions in a local neighborhood, we can come up with good bounding boxes. For example, here we can see that this cow can be formed by this region, this region, this region, this region, which all of them are regions of constant color. The other category of object proposal techniques exploits the observation that objects are distinguished from their background by strong edges. For example, this lady here can be distinguished by the background by this very strong edge, while the edges in the interior of the region of this lady are not so strong. So by using this information, we can come up with a scoring function, and we can score the importance of different boxes in the image. And then we can propose the most important ones. So after having extracted the object proposals, we can use the standard image classification pipeline in order to classify the proposals and to localize the objects. So what we do is that we take the image, we extract the object proposals, we take each object proposal, we create a bigger window so as the proposal will contain the entire object, then we crop it, we scale it so as to fit to the input of the network, and then we feed it to the network. And the network can classify the sub-image whether it belongs to one class or the other. Here we can see an example of image classification where we see that this scene has been classified to wall, table, chair, curtain, railing, shelves, and other. Or here, the next image has been classified to lighthouse, tower, building, sky, dome, house, etc. And here we can see the result of object detection. Here we apply the technique to each frame independently. And we can see that we can classify the frame to some classes, and also we can localize the objects in the image, in the video frame. So this was what I wanted to present you for object detection and image classification. And now let's go to how we can teach machines to recognize actions. There are three types of methods. The first and the simplest one is based on human body silhouettes or the skeleton of the human body. The second type of methods is based on space-time interest points. And the last one employs neural networks in order to combine all the processing steps to one network. Let us start with the silhouette or skeleton-based methods. These methods define an action as a sequence of successive human body poses. For example, here we can see a person walking, and if we are able to extract the human body pose to distinguish the person from the background, we can come up with a set of human body poses. So we can see how the human body evolves during time in order to perform the action. If we are able to do this, then an approach to encode these human body poses is to use a set of prototype human body poses which can describe all possible poses that the human body can take. So after doing this, we can encode the action video with a vector, and we can use a classifier to classify the video. What's more, we can use multiple cameras in order to better describe the action from different viewing angles. For example, if we see a person walking and we see him from a side view, the body poses of his body have different shapes when compared to if we observe him from a frontal viewing angle. So by doing this, we can, in this particular example, we can classify each of the videos independently, and afterwards we can combine the classification results in order to obtain a more robust solution. Here we can see an example of this method. We can see that we can recognize both actions and interactions between persons. Here is an example of the multi-view approach. As you may have observed, these methods cannot be used in the cases where the background is not very simple. So what we can do for videos like this, here we have a non-constant background, we have multiple cameras capturing the action, the cameras are moving, so this is not a very good video for the previous methods. So here we can borrow ideas from from image classification, and we can see that we will describe the video using local shape and motion information of interest points. Here we can see a video frame. Here we can see the video frame pixels which have been decided that are important for the action. For example, here we can see this is an action of hand clapping, and here the detected interest points are at the hands of this woman. Also, this is a nice example. We can use this for other types of actions, for example, for facial expressions. What's more, we can use the trajectories of video frame interest points. For example, here we have a complicated action, I think. And here we can see the trajectories of interest points. You can see that there are some red and some green dots. So the green dots are the interest points which have been decided to be more important for the action. And you can see that most of them are placed on the person. Here is another example of the first video. And the importance of space-time interest points is very high because we reduce the number of pixels that we use for describing the action. This is very important for computational reasons because imagine that if we have an HD video, it will have 1000 by 1000 pixels for, let's say, 100 frames. So the number of pixels that we would want to describe is enormous. By doing this, we use a subset of all possible pixels, which is very important for speeding up the methods. So we have a video. We again extract descriptors in the neighborhoods of interest points. We use again a set of prototype descriptors, and we create a histogram-like representation. This can be used for classification of the video using a standard classifier. Another way to extract geometric information for the videos, for actions, is to use stereoscopic videos. Stereoscopic videos are videos which are captured by two cameras which are placed the one next to the other, and the distance between the cameras is similar to the distance between the eyes of the human. So having these two videos, we can decide which is the relative distance of a point in the scene with respect to the cameras. And for example, this is the left and the right video frame. Here is the disparity map. This is how it is called. And here we can see that we can segment the two persons from the background. So what we can do is we can segment stereoscopic videos in several disparity zones and describe these zones independently, or to combine the information depicted by different zones. And here is how we can use CNNs in order to recognize actions. As in the image classification case, we have here a video. We have a set of 3D filters. We convolve the video with the filters for a set of layers, and then we use some fully connected layers. And here is another way to do this by using 2D convolutions. Video frames, a set of convolution images which have been created by using 2D filters, 1, 2, 3, 4, 5 layers, and then we have the fully connected layers. That's it. Thank you for your attention.
Okay, thank you. And let's have the second talk and then afterwards discussion. And the next speaker is Svetlana Vetchinnikova, and she will talk about modeling language as a complex adaptive system.
All right, so indeed, modeling language as a complex adaptive system. I decided to choose this topic for several reasons. First and foremost, since it's quite interdisciplinary, and it's a very interdisciplinary group that we have here, and I'm very much looking forward to your comments, whatever you will have to say. It is also something that's, I think, quite recent in linguistics, very recent advance, and something which is also close to my interests. As I have been saying here, I'm quite theoretical, so I like theoretical models, I like theorizing, conceptualizing, and this is an exercise in theorizing in a way, or this is going to be. Right, so the way I'm going to structure the talk today is the following. First of all, I'll say a couple of words about complexity theory, or at least the way in which it is adopted in linguistics, because certainly complex systems have been studied in many fields of science. Linguists are quite late in adopting the theory, and the way we've done so, this is what I'll be showing. Then I'll answer the question in a way, why apply complexity theory to language? So what is it in language that makes us think that it can be modeled as a complex adaptive system? Then I will model language as a complex adaptive system, or at least show a couple of ways in which it can be done so. I'll show a couple of examples of properties of complex adaptive systems that language seems to be exhibiting, and this is something well worth discussing. And finally, what does it give us? Applications and implications of modeling language as a complex adaptive system. All right, so what is a complex adaptive system? It's quite simple. It's basically anything which consists of multiple types of elements in continuous interaction between each other. So basically anything that is comprised of different types of elements can be modeled as a complex adaptive system. So biological cell would be a complex adaptive system, a biosystem would be a complex adaptive system, or at least can be modeled so. Complex adaptive system involves multiple embedding and nesting. So an element or an agent of a complex adaptive system can itself be a system, and so on and so forth. Another interesting way of looking at a complex adaptive system or defining it would be as a set of variables that interact over time, as Kees de Bot and colleagues have done. In this way, or this way of defining complex adaptive system means an even greater number of possible applications or modelings. So even many other situations or many other interactions can be modeled as complex adaptive systems in this view then. The rationale behind modeling something as a complex adaptive system. Basically, a complex system is a regularity that's identified by scientists. And as I've already mentioned, anything which involves a complex interaction of different types of elements over time can be modeled as a complex adaptive system. But the important thing is that if something is structured as a complex system, then it's probably going to exhibit the behavior of a complex adaptive system, which can be described by a number of properties. So it's the properties that we would be interested in here. And again, modeling something as a complex system then means cross-disciplinary comparisons. So we can, for instance, compare bed of flocks with how language behaves, or a living cell with again a language, or a bed flock. In terms of properties, so here the important word is properties, I would suppose. Here is a number of properties that are often discussed in relation to complex adaptive systems, and I think most of them will be very familiar to you. Again, they come from very different sciences. So first of all, sensitive dependence on initial conditions, and a very famous or well-known article by Lawrence dating back to the 70s, does the flap of a butterfly wings in Brazil set off a tornado in Texas? And I think the title of the article very well describes what is meant by sensitive dependence on initial conditions. It basically means that something very small, very small action can in the end going through different loops, iterative loops of interactions, can in the end create a very big event. So how a big event can be created by very small events. Secondly, non-linearity, and again a very well-known phrase from Greek, or example from Greek, let's put it that way. The act of playing the game has a way of changing the rules. This is how he describes the property of nonlinearity, and has done so by describing the act of playing hockey. So velocity of the puck depends on friction, friction depends on velocity, and there is constant interaction within it, between them, and therefore it's very difficult to predict the result in the end, because it is a nonlinear system. Phase transitions, quantitative change can in the end bring a qualitative change. For instance, constant heating of water changes water into vapor. Emergence, as the picture shows, there is a traffic jam, and the agents of the traffic jams are cars, but the traffic jam is not the property of the car. It's the property of the traffic jams, of the interaction between them. So traffic jam emerges as a result of interaction between the cars, rather than is the property of each single car. And I will return to this property when I will be describing the behavior of language, because I think there are a lot of things which can be regarded as the property of emergence. Coherence in the face of change. Despite the perpetual dynamics and continuous interaction, there is a certain kind of coherence that can be seen in a complex system. Scale-free self-similarity, that's also going to be quite important here in this talk, also called fractal scaling, and dating back to Mandelbrot in his 1982 book. in Mandelbrot's words, a fractal is geometrical shape that can be split into many parts, and each part of it would be a reduced copy of the whole. So an interesting thing to think about is whether certainly language can be split into many parts as well. And an interesting thing to think about is whether when we split language into different parts, whether each part of this language would be a copy of the whole. But we'll return to that. Self-organization, flocking behavior, for instance. The idea is that birds did not mean to flock. This behavior emerged as an interaction between the birds. So the property of self-organization, and certainly evolution, which happens spontaneously through adaptation. So there is no global design; it just happens. So very briefly, these are the properties of complex systems that are often mentioned in relation to modeling, and these are at least the properties that I can say are mentioned when in linguistics. And again, your feedback is very much welcome as to how other complex systems in other scientists exhibit these kind of properties or not, or whether there are any other properties. So now moving on to the question of why a complex adaptive system perspective on language. I took some time to think about it when preparing for this presentation, and I think the decision that I've come to is that the reason why it seems to be in the air, and the reason why linguists seem to be turning to this perspective is actually the fact that complex adaptive system viewing is a logical continuation from a theoretical development that linguistics have been undergoing throughout the last 20-30 years. And it is a development, a change from generative or Chomskyan paradigm to usage-based grammar and usage-based linguistics. And here in this table, I'm comparing and contrasting the Chomskyan approach or the traditional approach to language and the usage-based approach. And you will see that in the usage-based approach, complex adaptive system perspective is natural and very much obvious. So in generative linguistics or Chomskyan linguistics, we tended to make or used to make a distinction between knowledge of language and or language competence and language use or performance, which means that there is some kind of language which we all have somewhere. It has an innate nature, so it's innate, and it makes us use language in different ways. But performance is only a reflection of this competence that we have, and it's never comprehensive. So we can basically, it means that we cannot draw conclusions about language on the basis of performance only, because it's only a reflection of competence. In contrast, in usage-based linguistics, language knowledge is the accumulated experience of this language, which constantly builds up. So basically, it means there is no language competence, or there is no some kind of thing in our mind, in us, that lets us use language. Language use is the accumulation of all the previous uses. And language at the communal level, language as, let's say, English, or a language as a concept, it emerges from the interaction of the individual languages. So language does not really exist away from usage. Back to Chomskyan linguistics, grammar leads to usage, so we have grammar, and we are using grammar in order to use language. In usage-based linguistics, grammar emerges from usage rather than exists independently of it. So basically, grammar in usage-based linguistics is only a description of all the regularities that we can see in language. Grammar depends on usage, or it's just the way we describe language. And so in usage-based linguistics, grammar is emergent. And let's go to the next slide, another set of pictures. And it continues the discussion of the usage-based paradigm in linguistics. So usage-based theorists would state that use is basically the same, equals acquisitions and equal change. So every time we use language, language changes. As Larson Freeman, for instance, wrote in 1997, quite long ago, but it's still very, very relevant. Every time language is used, it changes. As I write this sentence, or as I speak here now, and you're listening to me, we're changing English. So language changes with every instance of language use, rather than it exists separately from usage and lets us use language. Therefore, second language acquisition, for instance, would also equal language use. So the way a second language user uses language is the state of his acquisition at that moment, and it also equals change or development in language. So how does language develop? How patterning in language evolves? There are two processes, or two very important processes, which influence the way language develops and the kind of patterning that we start seeing in language. These are cognitive processes, so those cognitive processes that each of us has, they influence the way we use language. And there are social processes, so all those social principles of social interaction between human beings, they also influence the way language is used. And through continuous interaction between cognitive and social processes, language evolves and emerges in the form that we see it. One thing which is very natural to language is emergent patterning. So let's put it very abstractly and theoretically. There are features, or there are elements A, B, C, D, and through usage they become glued into certain kinds of patterns like A, B, B, C, C, D, A, etc. This is partly explained by the cognitive processes, and one of them is sequential processing, and it means that something that we use together gets fixed into a certain kind of pattern. And again, if we then return to grammar and our conception of grammar, grammar of language is the description of its patterning. So it is the description of how of the patterns like A, B, B, C, D, B, C, D, A, which have emerged through the interaction between cognitive and social processes. As you can see, then a conception of language, complex adaptive systems modeling seems very natural. So it is a continuous interaction of multiple elements of different types, and whatever we'll get in the end is an emergent process. Right, so in which ways can then we model language? The easiest or the most obvious way we can see language as a complex adaptive system is, of course, as an interaction between the speakers of the language, right? So a speaker of the language would be an agent, and language would evolve in the interaction between agents or language speakers. Language speakers form different communities of speakers, and this we can think of these different groups of people as different levels or different planes. So there are, of course, different groups, like a nation, for instance, all the population of the country, and one population of the country usually speaks some kind of standard language, let's say Finnish in Finland, and that would be a language, but there are different dialects in Finnish, which are used by different special separate groups of people, and that would be modeling language at a bit lower level. And we can go all the way down to individual languages. This is something which is not often done, so very often we stop somewhere at a level of a community, but do not go to individual languages, not thinking that actually each e-dialect can also be quite different from any other e-dialect. So just like dialects might differ from each other, or just like languages might differ from each other, the different ways each of us speaks language might also be quite different. So e-dialects might also be quite different, as I'm going to show you in a moment. So one way to model language as a complex system would be across different speech communities, starting from the top and top down, then thinking of local communities and language varieties, such as if we talk about English, British English, Indian English, New Zealand English, Jamaican English, etc., going to dialects and all the way down to individual languages. At the same time, it has been shown in linguistics that languages also differ by discourse communities. So, for instance, we scientists use language in a certain kind of way, and it will be very different from the way businessmen use English. And you would even be able to see differences at the level of grammatical constructions, or at the level of preferences, at the level of lexis, at the level of at very different levels, which are usually thought of as basic in language, and as common to all discourse communities. In fact, discourse communities can differ by these basic features. Each discourse community has certain kinds of genres that they use. So, for instance, in science, we have a genre of scientific presentation, or an article, or a grant proposal, and all of these genres would also be different from each other in terms of the specific features that are used in each of the genre. And again, we can go down to all the way down to individual languages. We can also model language across time scales, and here we would start with the bottom and go upwards. So language is created starting from, or language in use is created starting from neuronal oscillations, then to a speech event. Then we can also talk about language across speech events, so something that's remembered from one speech event and brought into another speech event. And of course, we can talk about the history of the language. That would be a historical scale. So starting from a very short time scale of neuronal oscillations and going all the way upwards to historical time scale. At each of these time scales, we would be able to observe different language phenomena. So language phenomena which are present at the level of neuronal oscillations are not present at the level of the history of English. So at the level of the historical time scale, we usually talk about such processes as language change and grammaticalization. And within a speech event, we talk about such phenomena as accommodation, or social construction of meaning, or social negotiation of meaning. And at the level of the individual or individual speech, then how, for instance, somebody's previous language background might influence the kind of choices that I'm making online. So kind of online time scale would also be quite different. We can also model language across levels of language organization. So we have phonology, morphology, lexicogrammar, textual structure. To sum up, to make an interim summarization here, we can talk about language at 3 dimensions. The social dimensions, as we have seen, language can be modeled across different communities of speakers and all the way down to individuals. So that would be planes of language organization. We can talk about the temporal dimension, we can speak about different time scales of language representation, from neuronal oscillations to the history of language. And we can talk about the structural dimensions, that would be levels of language representation organization from, again, phonology, for instance, to the structure of the text. And how does complex adaptive system come in here? It would be intriguing to think that the relationship between these different planes, scales, or levels, in each case, that it can be described by the properties of a complex adaptive system. So the relationship between them would be that of emergence and perpetual dynamics, and even scale-free self-similarity or fractal structure. So the idea or the question is whether indeed we can model the relationship between the planes of language organization, the time scales, and the levels of language as fractal. So can, for instance, the way we see language as an individual language, or the individual language, does it show the same properties or as language from a historical perspective, only kind of as a reduced copy of that whole? This is a hypothesis, and I'm going to show a couple of examples in relation to this hypothesis, let's put it that way. So when talking about, and now I'm only going to focus on planes of language organization, so you remember that social dimension rather than time scales or levels of language organization or the structural dimension. And I'm only going to talk about the cognitive plane, or the level of the idiolect, and the communal plane, or the level of the language of the community, whatever the community is. For instance, it can be, for instance, our club might be very well described as a community. The whole Finnish nation can be described as a community, or scientists as a whole can be described as a community, or then, let's say, linguists can also be described as a discourse community. So how does this communal plane or language of a community relates to the cognitive plane or the idiolect? One way to think about it is to try to think of how emergence, or the property of emergence, comes in here. So if we model language, the relationship between these two planes as a complex system, then it is going to show the property of emergence, and then the language at the communal plane will not be the sum of idiolects, but will be emergent from them. Therefore, we'll be able to see certain kind of properties that will only be present at the idiolectal or individual plane rather than at the communal plane, and there will also be certain properties that will be present at the communal plane only, but not at the individual. And as the example that I've shown before of a traffic jam, that traffic jam is not the property of a car, but of the interaction between them. In the same way, certain kind of properties that communal language exhibits might not be a property of individual languages, but might be emergent at this communal level only. The data that I'm going to use, or the data that I'm using to operationalize this kind of relationship between different planes of language representation, I'm using the data from just one blog, it was a very active blog with more than 4,000 commenters, or more than 4,000 participants, and it's got more than 7 million words in it, in more than 74,000 comments. And this, the data that I'm going to use, we corpus linguists call it a corpus. It contains only comments, so it does not contain posts. It only contains those small comments that readers of the blog or the author of the blog post on the blog. So, for instance, their length is on average about 100 words, but it kind of varies from one word, like great, or just a smiley, to maybe about 2,000 words. So some blog comments can be quite long. Since this blog has been so very active and with many contributors, many followers. There are it can be divided into several individual parts. So I can track down individual people who have contributed to this blog. And the author of the blog in particular has contributed almost 2 million words in comments to this blog. I call him Joseph, that's a pseudonym. There are also 5 commenters who contributed at least 150,000 words to this blog each. And there are other about 20 commenters who contributed quite substantial amounts of language to this blog too. So I can kind of treat them as language represented at the cognitive level. And so each of these languages is then treated as the cognitive or individual languages. But when I take the whole blog and remove all the comments written by very active contributors, those 24 contributors who've contributed many thousand words. When I remove their comments, I get the communal level. If I left those comments in my communal representation of the blog, then they would kind of skew my calculations. So I have the cognitive level or the individual level as represented by several individual commenters, and the communal level is represented by non-24 corpus, or the corpus except the most 24 active commenters. There's also a microsocial level, which I'm not going to focus on very much here, but it is the discussions between the 24 most active commenters. There are certain kind of things that are going to evolve between in those interactions too, but again, not going to focus on this here. Just to give you some taste of the data, here are some examples of the individual phraseology or the phrases that individuals use on their own. So these would be phrases that these individuals use but others don't. So think about the data. It's 7 million words, which means it's basically about 70 books. If one book is about 100,000 words. So and certain phrase only occurs in one author but not in any of the 4,000 other authors. That's quite interesting, isn't it? So here is one of such phrases. It's just to be sure, and Joseph uses it 130 times. Of course, he has contributed a lot of words to this corpus, about 2 million words, but still 130 hits or 130 instances is quite many. And also he tends to use this phrase at the beginning of a comment to clarify possible misunderstanding, for instance, or to specify what is it that he means. So for instance, he would say, just to be sure, this article was meant as a joke. And the tag with 3 dots that you can see at the beginning is meant for the beginning of the comment. So whenever this tag occurs, it's the very beginning of the comment that he's writing. Or then he might say, just to be sure that it's not just special relativity, but also general relativity, where, etc., etc. So here's just a few examples. This phrase is used by 2 other active commenters, twice by a French commenter and once by an American commenter, and occurs once in that non-24 corpus of the communal plane. So it's used by 3 other people only, and but it can be that they are also using this phrase, but not in this corpus, or it's also possible that they have adopted the phrase from the author of the blog, from Joseph, because he is so important in this blog in particular. Just to give you an idea of how it looks, this is only Joseph's uses of just to be sure, and it occurs many times over. Just to be sure, just to be sure, just to be sure. You should not be left in any doubt. Any of us has certain kind of expressions that we use over and over again, and there are a lot of such expressions, only that we don't notice them at all. and we use them for certain very specific functions. Another example from a Greek commenter, Greek speaker. One of her favorite, or well, I wouldn't really call it a favorite expression because it only occurs 6 times, but it's an expression that's peculiar to her own usage because it does not occur in other comments. So she says, "We live in interesting times," and it seems like she uses it as a very convenient opening or closure of a comment. So she might start, and this is also quite understandable that we often think how to start an email, for example, or how to start a comment, or how to start something, or how to end it. So these are quite frequent considerations that we're going through. So this is her solution to the problem. She can start a comment by saying, "We live in interesting times," and then continue a comment by saying something else. I think I have not yet mentioned that the author of the blog is a Czech physicist. So it means he's a non-native speaker of English. And the previous slide showed the phrase of a non-native speaker of English too. But so that you do not think that it's only non-native speakers of English who have certain specific phrasings or certain favorite phrases in their repertoire, I'm now showing you an example from a Canadian English speaker. And his expression that nobody else uses is "know for a fact." And this expression again is quite fixed in his particular usage. He says, "I do know for a fact, I know for a fact, I know for a fact that the toothbrush," or something. So now that I know for a fact that your book is, I know for a fact that Josh Hum is, I know for a fact that it will never, I know for a fact that it really, really, etc. So it's a very fixed pattern. This is the way that I would describe it. So it occurs verbatim, and it's several words in immediate co-occurrence, and for that reason it's quite peculiar. So, and there are only 6 commenters in more than 4,000 commenters who use this phrase as well, but each of them only once. There are also individual preferences, those phrases that certain individual language speakers use very often, but other speakers might be using it, but not so often. So kind of grammatically, or in terms of, it's a very, might even be a very trivial phrase, but it's something that you use with increased frequency in comparison to other speakers. So one of these individual preferences for Joseph was "nothing to do with." So he liked to say it's got nothing to do with X, or it's got nothing whatsoever to do with freedom. So that would be the only variation, and it occurs 470 times in his usage in certain kinds of variations. Right, and again, to show you that not only non-native speakers have individual preferences, I'm showing an example from the usage of an American speaker. And this time it's the phrase "there is no such thing as," and again you can see that she's quite consistent in her usage, and again it's a very fixed phrase. There is no such thing as carbon neutral, there is no such thing as one right answer, etc. There are 10 more commenters who use it 1 to 3 times, and it also occurs in the non-24th corpus. So again, it's not something that does not occur at all in anybody else's usage, but it occurs, she kind of likes this particular phrase because it occurs in her own usage much more often than in anybody else's usage. So I've now shown you some examples of very fixed phrases or phrases that are specific to an individual and individual preferences. And now I'd like to focus on the distribution of variants of a very specific construction and how this variance will be distributed across different individual languages and the communal plane. It is adjective that construction. It's actually very frequent, and you would recognize it immediately because I'm sure you use it very often in your own writing too. So, for instance, it is likely that the trip will be cancelled. It is odd that such a town has such a view. It is plain a mistake has been made. So it's, as you can see, very often used for evaluative function. So we kind of attribute an evaluative feature or value to a certain kind of utterance. And that's one of the reasons why it's so often in academic language. This construction is described in grammatical terms as an anticipatory it construction, and it's also described as a grammar pattern by Francis et al. Francis et al. Also describe adjectives that fall within this construction in several groups. So the adjectives usually fall into the group likely or interesting, obvious, marvelous, awful, important, and relevant. So how is it distributed in individual languages of the block? When we look at Joseph's use of the construction that is adjective that, there are a lot of adjectives that he uses in these constructions. Most of them are shown on the slide, but there are also 42 more adjectives that occur only once in his usage. What's interesting about this distribution is that there are some adjectives which are very frequent, which he uses very frequently, like it's clear. It seems like it's clear that is the most frequent way he uses this construction. And he also says very often it's plausible that, it's obvious that, it's likely that, it's true that, it's unlikely that, etc. So the important, it's very important to note about this distribution of adjectives in the construction that it follows a Zipfian distribution, Zipfian type token distribution of adjectives. This is a power law, and such power laws have been described in other sciences like a Pareto law or an 80-20 law, meaning that some things occur much more often than other things, and there is a huge tail of one-off occurrences. And all of the examples that very often given are things like when we think about online shops, then Amazon is known to everybody, but there are a lot of shops that are known to just one or two people, or maybe more, but again, not to everybody. So, but when we look at the distribution of adjectives in this construction in other speakers, we see exactly the same distribution. Well, not exactly, but approximately the same distribution. It's still a Zipfian distribution, so there are adjectives which occur much more often than others, and there is a long tail of one-off occurrences. And it seems like this kind of distribution looks like scale-free self-similarity. So when you split up language into several parts, each part can be described by a Zipfian distribution. And if we look at the distribution of adjectives in the same construction at the communal level, we again get the same distribution, that some adjectives are very frequent, and then there is a long tail of one-off occurrences. Frequency distribution of words in different parts of language have been described by many linguists. So, for instance, frequency distribution of words in any single text seems to be following a Zipfian law, like the text studied was Tom Sawyer. Any corpora. Type token frequency distributions of verbs in verb argument constructions, for instance, verb locative construction. I'm going to the shop, right? So the verbs that can be used in this construction can be go, run, jump, ski. But the frequency with which different people would use these verbs in these constructions would also exhibit a Zipfian law, a Zipfian distribution. So the question to ask is whether conformity to Zipf's law can be treated as a symptom of the fractal structure of the system. When we look back at the specific adjectives that are used by different individuals in the construction, it seems that there is wide inter-individual variation as well. So different people would use different adjectives. That's the bottom line. And it's even more interesting to have a bit larger view at the construction and see whether kind of to look at the prolonged construction and look at the it is adverb adjective that construction. So for instance, it's quite conceivable that, so add an adverb into the construction as well. And then you'll see that certain different speakers would have very fixed preferences for certain verbs and adjectives that they would use. So for instance, Claudia would use it's quite conceivable that, and it's even worse that. Don would use almost certain that and also possible that. And Laurie would use quite possible that. And if we look at Joseph's use, then his favorite combination of adverb and adjective in this construction would be still true. So it is still true is the most frequently occurring variant of the construction. And the most important thing here is that just imagine if one individual uses this combination of words, it's still true that over and over again, hundreds of times, then it's no longer a grammatical construction for him. So he does not have to think of which adverb to put there or which adjective to select to complement this construction, but he would just kind of retrieve it as a whole from his lexicon rather than put it together from scratch at the time of use. So it's no longer a grammar pattern, but rather a very lexicalized, a very lexical item, just like any word would be. Therefore, when we talk about it is adjective that construction, it seems like different speakers would have preferences for different verbs, different words, adjectives and adverbs to fill that construction, and they would be lexical patterns. In academic English, if we go up in our model to the next level of representation, then in academic English, for instance, there is a tendency to use this construction for evaluative function. And only at the communal level of English we would get the grammatical structure of anticipatory structure. Certainly each individual speaker, since there are so many one-off occurrences of adjectives in their repertoire, certainly the grammatical pattern is also available to them, only that some instances of the construction have got fixed so much that they're no longer instances of grammatical construction but are separate lexical patterns which they use independently of the grammatical structure itself. So grammar can be thought of as an emergent property arising at the communal level, in this case anticipatory structure. One more mention to make here about the scale-free self-similarity. I have mentioned one, Zipfian law, which seems to describe the patterning across different scales. One other thing would be fixing, but now we need to think about time scales rather than cognitive and communal plane. So you have seen some examples of fixing in different individual languages. So different speakers start to use a construction in a very fixed form. So the kind of the elements of the structure get fixed in a lexical patterning, in a lexical pattern there. A very similar process is described and observed at a very different time scale, at a historical time scale, and it's termed grammaticalization. There again, with frequency, certain kinds of certain words fuse together to form larger chunks. So, for instance, a very well-known case of grammaticalization in English would be the case of going to. So, because be going to initially was a verb of movement. So, I'm going to see me, or I'm going to the movie. I'm going to do something meant the moving somewhere to do something, and only later it developed into the future expression as I'm going to give the presentation or something like that. And such a development in language such a development towards a more fixed construction also meant a phonetic reduction in this chunk. So be going to is very often now used as gonna just. So this is a grammaticalization path or a trajectory of language change that is described at the communal plane, but fixing the way we have seen it in the examples from individual languages seems to be very similar to this type of process. So would fixing at the individual level and grammaticalization at the communal level exhibit the same scale-free self-similarity as can be seen in other complex systems? My conclusions in terms of applications and implications. When we or modeling language as a complex adaptive system might help us to make predictions about the future of English or the future of in language use. So for instance, a very current phenomenon of English as lingua franca. English is used between speakers who don't share a mother tongue. Nowadays it is mostly used as a lingua franca because there are more non-native speakers of English than there are native speakers of English. So what's going to happen to English then? How is English going to change? What's going to happen to language when it goes global? Anna Marnin asks. Will a quantitative change lead to a qualitative change in this case as well? Where is there going to be a phase transition that we can predict? These are the kind of questions that modeling as language as a complex adaptive system might pose for us. There is also a theoretical promise. So for instance, one might make other observations of what grammar is, and one question to think about is whether grammar is an emergent property of language at the communal level. If language is split into parts in a number of ways, will in each case a part be a reduced copy of the whole, a fractal? That's another question to think about. I'll stop here. Thank you.
Thank you. Alexandros, I was wondering, where is the bottleneck in this at the moment in this image recognition or action recognition? Is it computational power or algorithms or somewhere else, if you consider?
Yes, actually, this is a very good comment, and you gave the answer. The bottleneck is the computational complexity of the methods. So what we do until now is that we create very complex and very successful techniques, but we need time in order to calculate the result. And this is a problem for real-time applications. So in the last 5 years, there is a very big attempt from the entire community to create very powerful machines, which can be used in order to calculate very fast, complicated algorithms. I would say that the current trend is to use massive data, massive size of data, train very complicated models, and try to do it very fast in the test phase, in online application. But I think that we need 5 to 10 years so that the computational infrastructure will meet this need.
Svetlana, thanks. That was also very good. What about spoken language? Like, I guess there must be differences between written and spoken language in terms of your modeling, and for sure spoken language must be harder to research in such a quantitative way, but and maybe some things that are present in spoken language in a non-verbal way, even in the communication between humans, are somehow becoming also into the written discussions, what you were analyzing. So can you comment on that? Just briefly, what about?
These kind of calculations are possible with spoken language as well, only that the corpora will be quite a bit smaller. So for instance, we do have a 1 million corpus of English as lingua franca in academic settings. That's also quite a lot. Only that what we don't have maybe is then that amount of data from specific individuals. And the problem with collecting spoken data is that it requires transcription. So it requires a lot of the work of a research assistant or many research assistants. For that reason, it's of course much more difficult to compile. And for such kind of ad hoc questions that, for instance, there is a hypothesis and I'd like to study it. It's much easier to find written data. At the same time, blog data is somewhere in the middle between spoken data and formal genres like an academic article. What you'll get in formal written genres is that is a lot of editing and a lot of revision cycles done by the writer, the individual, which would also reflect language regulation that's done in academia, for instance, if we're talking about an article, which would not reflect, therefore, the kind of representations that are natural or are frequent or are especially preferential for the specific individual. And for that reason, kind of genres which are more spontaneous, like blogs, are preferable in answering these questions. But certainly I'm sure that in spoken language we're going to see the same kind of patterns, that there will be a lot of fixed phrasings. And this is in general what I have found in my own work, that at the level of the individual, the language gets very fixed. There are a number of sometimes, and one way it does get fixed is verbatim, that it gets fixed into a noticeable pattern, like there is no such thing as, which is easy to notice. But there are also a number of very abstract ways in which patterns get fixed, which are much more difficult to observe and to notice, and therefore we don't notice them, but they are very fixed. Just a few patterns that each of us has in their repertoire.
Questions? I have one for Alexandros, which sort of relates to the previous question. Are there real-life applications of this kind of methods that are in use but we don't actually realize? So, or are they so complicated that they are not really in use yet?
These attempts have been very well integrated in our daily lives. For example, all of us have some smartphones. So some of us we don't have, but most of us we have smartphones. So when we try to take a picture, we see that there is a face detector there, or there is an autofocus, which means that there is a software in the smartphone, and this software has decided that this is the object that the camera should be adjusted so that the view, the picture that will be captured will be nice to the viewer. Other applications are surveillance applications, where we have, for example, fingerprint recognition, which is another type of objects. So we want to distinguish between different fingerprints. Or in airports, where we have the automatic passport checking. We put our passport on top of a sensor. The sensor can take a picture of this. The machine inside there is software inside the machine which takes a picture of your face. It compares this picture with the picture in the passport, and there is a verification of that the person who tries to enter the secured area is the person depicted in the passport. So there are many applications where we can see examples of such methods, and I believe that we cannot recognize that these applications exist.
Okay, but in the smartphone, the computational capacity is not
This is why it is restricted only in object recognition and autofocus. Imagine that in the future there will be some smartphones which will have a computational capacity of very good PCs. For example, my smartphone now is better than my PC when I was a student. So, and there is another trend which there are some thoughts that we can capture the images or videos, we can transmit them to powerful machines running in the cloud. The computation will be done there and the result will transmit it again to the smartphone. So there are several ways to integrate smart processes in our daily lives.
That's interesting. And then I have a question to Svetlana. So I guess in a way you could say that you can't say that some way of using language is wrong and something is the correct ways. They are just different ways. Is that the case?
There are more common and less common ways of using language.
Okay. That's a good way to put it. And then another question. You had these word distributions which follow the zip law. Now, is it the case that when somebody is starting to learn a new language, then he or she knows just a few words. This is a table, my name is Pekka, and so on. So you can't really see very clear distribution. So does the word distribution converge toward the zip law when a person learns the language better and better?
I think in classroom-based language learning, the trajectory of acquisition would be quite different just because it's no longer a complex system. It's not an open system any longer, right? So you learn just what you are presented with. And when we are talking about language evolution or language immersions in naturalistic settings or natural language evolution, when an individual is exposed to some kinds of language uses, to some kind of language forms, then the ones that he or she are going to learn would follow the Zipf-in distribution. So in classroom, then in classroom setting, you would learn. You are not exposed to, or at least in the first, if we're talking about just the first classes of language class, then you are not exposed to as many. That might be the reason why it's intuitively not going to follow Zipf's law, at least at first. But whenever you start to get exposed to the all language variation that we are continuously exposed to, then our language acquisition, at least hypothetically, going to follow the same paths.
First of all, I know that this pattern recognition is a very active field nowadays from the technical point of view, for example. But is it so that it has already reached the level that if you want to see something, you will see it? I mean, it is possible already. I mean, if you know what you want to see, then you will see it.
How do you define seeing? I mean, you have an image and you want to see if there is an object in this image.
Yeah.
Or a specific type of objects, for example.
Yeah, for example, in this pattern recognition, if you want to see a man, then you are able to do it.
If the man is...
But but of course it's much more difficult to say what do you see. Nobody knows. I mean, in general.
Of course.
But if you want to see a man, you will see it. If there is a man. So that's possible by the modern technology already very much. So
what you said is true, that if we know the object that we want to recognize, then we have a very good performance level on this. For example, there are cases where machines can outperform humans on this. But the problem is that we cannot define a set of all possible things to recognize or the interactions between them. So the complexity after a point is very high, and we as humans can do this because we have been trained myself for 31 years. So after seeing some objects and the interactions between them, I can recognize what will happen, for example. But machines have not been used to be trained in this extent, so the problem is the complexity. In which level we want to reach in terms of complexity. If we want to recognize, let's say, 100 types of objects, in this case, machines are extremely good for this.
Yeah, you see that it is a general problem. I mean that if a man, in general, he doesn't see what he doesn't know. He only sees what he knows. I mean, if he sees something unknown, he didn't see. He doesn't see it. I mean, yeah.
In this case, what we do is that we try to connect it with something that we know, even if this is wrong. And after being exposed in this kind of objects for several times, then we can distinguish it from what we know. Then we can create a new class of objects.
Objects, out of that.
Yes.
Yeah, by the way, I mean, to the second talk, if you, I have the feeling that this, if one looks at the block kept by string theorists, it must be a kind of dialect they speak. I mean, very much. I mean.
I have told you more information about the blog. In fact, they discuss very different things, and physics is not one of the most common topics. So they actually discuss politics and especially global warming. There are, of course, a lot of questions, a lot of physics questions, but...
Yeah, I have the feeling that it must be a very narrow, even a very narrow dialect with a very idiomatic expressions, I mean, used in the text. And very different from the spoken language as well.
As I'm saying, they are discussing very different questions, and for instance, one thing that I had to do to determine the native speakers in the corpus or the first language backgrounds of other speakers, I had to look for such things as my language or my mom or my dad, or for instance, an expression that does characterize US speakers would be here in the US. So if somebody uses here in the US a lot of times, then it's 99% that it's going to be an American. This is what I get. So meaning to say that they do talk about their moms and dads and where they live and how much rain it was there. And so it's a blog, and it's in very many ways it's close to spoken language. There's been research on the comparison between the language or the way it's used in blogs and written language and spoken language, and it seems like it is somewhere in the middle between the two. So there are a lot of spoken components, but at the same time, when you think of, let's say, a research seminar on biology, is it going to be a dialect? There are very specific topics they're going to be discussing, and they're also even more specific than they're going to be discussing in the blog, because here they also kind of share some information about themselves and about their backgrounds.
Yeah, so thank you for the both presentations. They were very interesting. And Svetlana, I have a question. You talked about repeated expressions in one's own language. So is there cases, or would it be useful to check one's own language or way to use it for this kind of fixed constructions? And would it be useful for the communication to reduce them, or are they just there like helping our communication or our logic?
Reducing them would make a dramatical damage, meaning that we won't be able to communicate. Just because it takes a lot of time to put words together from scratch using the rules of grammar. So we just have to rely on our favorite expressions or these different kinds of chunks. And all of us seem to have different chunks, but it does not make any problem for communication because our comprehension is, or our understanding of language, perception of language is fuzzy. So we do not pass it into separate words or into the chunks that we know either. So we just approximately understand, and it's enough. So no, there is a lot of use in the chunks, or in the fact that language does consist of so many chunks. At the same time, it's also possible that one of the reasons, for instance, that it's difficult to find common language between different sciences is because they are like dialects, as you say. So biologists speak their own version of the language, linguists speak their own version of the language, economists speak their own version of the language, and there is a lot of common shared ground between them, but there are also so many differences that it's much more difficult to find the common language than between the speakers of the same discipline. That we definitely develop them. We develop the chunks, and we develop our own chunks as individuals, but we also develop the chunks within a discourse community, whatever that discourse community is, or inside a language variety, or inside a dialect. So there are different ways how people divide into groups by their activity, as scientists do, or by their locality, so where they live, by geographical location, and then we have language varieties. In whatever the way we divide into groups, anyway, we develop our own chunks inside that group as well, and therefore the communication between the different groups, whatever they are, again, is a bit more difficult than within one group. Just theoretically.
Okay, one follow-up question from your answer. So would it be possible to identify such, let's say, constructions or other elements of speech that are too difficult when we are trying to, let's say, communicate across science borders?
Right. So chunks that would pose some difficulties for understanding. That's an interesting question. The problem, I think, would be that these would not be any specific chunks, so it would not be possible to just remove those chunks and then the communication would become easier. But another problem would be that the different chunks in different groups or discourse communities might mean a bit different things. So, and that's a much more problematic thing, that if linguists by a certain chunk mean X and economists Y, then there is no surface difference, but there is a misunderstanding or a problem with some kind of understanding. But still, again, it's not any specific chunks that we develop, but it's the whole language which consists of different chunks. I've only been showing you verbatim co-occurrences, very fixed chunks, but there are a lot of abstract patterns. Like, for instance, it is adjective that construction is at least just a bit at a different level of abstractness. So it's more abstract than a verbatim fixed chunk. But there is patterning at even more and more abstract levels than this construction.
Okay, any other questions?
Thank you for your presentations. I have one question to each of you. So, Alexandros, your presentation made me think about all these promises that have been given for computation and computers since 60s or something, where all kinds of things were about 5 years away, like yes, pattern recognition from pictures and language recognition and translation and all kinds of things that are either very easy for human beings or at least sort of semi-easy, and turned out to be quite hard for computers. So it was much more than the 5 years that they were away. But now it seems that they are actually emerging, and could be that that's just the increased computational capacity. But at the moment, I guess there are machines that are good in one of these things that humans are good at. Will we ever get a computer or, say, a robot that is actually good in multiple things that humans find sort of just really easy? A 2-year-old can walk and talk a bit and recognize balls and animals and so on, but not a single computer can do that at the moment. Will there ever be a computer? And will the question then be just increasing computational capacity, or would there be something else as well?
This is a very good question. What we have described is a multitasking robot. It means that instead of running one software doing image classification, it can at the same time run another software doing object detection, another software doing action recognition, and so on. So if we think that we have good software, good techniques for doing all of them independently, and we can have an extremely good machine which has thousands of cores of processing units, and we can let it to run all of them in parallel. This would be the answer to your question. We can have machines which can do all of them at the same time. The question now is, how can this machine combine all these things, all these outcomes? And this is where the complexity of the pattern recognition outcomes, classification, action recognition, is very big. I mean, even the small kids can recognize a person, but I think all of us have seen the scene where a small kid sees his parent and runs towards to him or her, and it cannot stop, and it drops on the parent. It means that it is complicated even for the humans to do to connect different functionalities, and we are exposed to this environment, and we try to learn how to combine all these functionalities, and after some point, after adequate exposure to this complicated environment, we can deal with these relatively easy things, easy functionalities for us. So the complexity of combining things will be very big. Another thing that we should focus on is to let machines learn for a longer period, because what we do until now is that we have a very complex data set which contains many possible appearances of different things, different objects, different actions, and we try to learn this. So we are very good at this. We are very good at recognizing videos and images which are similar to the videos and images which have been used for training the machine. But the success of humans in recognizing objects, in understanding interactions between objects, between persons, between animals, between everything, comes with the very long exposure to the environment. So, as I said previously, we are exposed to this environment for several years before we can say that we can react in a satisfactory way with what will come to us or what we can see. So, computational power and very good algorithms and long exposure to the environment. I think this will lead to the success. Let's see.
Thank you. And then Svetlana, you showed us examples of constructions that were almost exclusively used by one person and not others. But have you seen examples of sort of contagious constructions where somebody, say Joseph, would be using a construction that would then start appearing in other people's usage as well? Because I think this contagiousness is a very common feature of language as well.
Definitely. So this is what happens at the microsocial level, which I did not focus on here, is that when people talk to each other and talk to each other very often, for instance, or even once, still we pick up phrases from each other. But if we talk to each other more than once, then they can be contagious, that you can actually start using the same construction. If you remember, one construction that I showed to you was nothing to do with, or nothing whatsoever to do with, that Joseph used quite a lot, 400 times or something. It seems like it is one of those phrases which has become contagious, because when I compared the frequencies of occurrence of this construction in this particular blog to the frequency of these constructions in other blogs, it turned out that it was much more frequent to this Joseph's blog. So other people might have started using it, or at least this is what we can say, is that it is more frequent than in different blogs. So what's possible is that when you read a certain comment or read a certain text, you can pick up some phrases, and so there's kind of this recency effect that you would use the same phrase that you have just read. And since Joseph uses this nothing whatsoever to do with so many times, then it might have occurred to many people that they have, because of the recency effect, they have read this construction, and it somehow stayed in their brain for some time, and then they also use it in their own writing. And then for that reason, it's kind of an accumulation of occurrences, again, across different speakers in this blog, that in the end showed this higher frequencies for the blog overall, something like that. But it's definitely true that we pick up phrases from each other. This is how actually change propagates, that there is some innovation, it's picked up and it becomes popular, in very briefly. But what's difficult to do is to track it down. So because when we notice a change, or when we notice that somebody started to use this kind of picked up a phrase, it's too late to go back and see how it occurred, how it happened that he or she started using the phrase, or that some phrase has become so frequent in the language. For that reason, we need historical data, and data spanning centuries, and then we can see diachronic changes. But again, these are changes at the historical time scale. How to track down changes to the short time scale. This is something quite interesting, but very difficult to do. And again, as I was saying, certain language phenomena would be existing at different levels. There are language phenomena that existed at historical time scale, but there are language phenomena that exist at short time scale.
Anyone else? Okay, you have one more.
So in pattern recognition or in the action recognition, you trained the neural networks with the 2D images, right? You had a big set of 2D images.
So we have a video can be considered as a success of several images. But there are several methods which try to recognize the action using one image only. But this is extremely difficult, and in order to tackle this difficulty, we use the entire video.
My question is that is there a way to use a 3D model to train your network? Just one model. You wouldn't need like many images. Some maybe artificial or somehow some other way generated 3D model, and then you would be able to.
If you remember the slide before the last one, there I was showing a 3D CNN, which means that you have a cube, which is a video. It is a three-dimensional signal which has pixels in X, Y, and T dimensions, time, and we can have three-dimensional filters which will convolve the video. So it means that we will place the filter in one video frame pixel. We will calculate the convolution operation, and then we will shift this in 3 dimensions: X, Y, X, Y, and T. So there are 3-dimensional models, but their complexity is extremely high for the current computational power that we have. Yes.
Svetlana, as a professional, so since grammar can be an emergent property on a communal level, do you think it's useful to teach it in schools?
Kind of teaching grammar at schools would be a shortcut to collecting millions and millions of language experience across time scale. Grammar is a description of the patterning that occurs in language. So there are 2 ways of acquiring this patterning. You can be exposed to this pattern, or you can be given a description. So it's just a shortcut in a way. But the problem is our description of patterning in language accurate? So that's the only question that I would ask. If it is, then that's a good description, and it can be a good shortcut.
That's a traditional problem in Finnish language teaching. We are learning the patterns, but not how to use them in practice. But I guess that's changing in schools also. There's less emphasis on the formal grammar, and they start with the usage of the language. Any other questions? Okay, if not, thank you very much for the interesting presentations and for the discussion from the audience. Thank you.